Dr. M. Subaya is an assistant professor in mathematics in LN Government College, Poneri. He has specialized on statistics interdisciplinary. Being interested in active research program and mathematical or statistical modeling, he has knowledge in operating various softwares on statistical tools and on technical computing. Having 16 years of teaching experience, he has published papers in 8 national and international journals, and has also presented papers in 10 national and international conferences.
Welcome to UGC lecture series on mathematical sciences. So, in this topic, we are going to discuss two important metrics for evaluating point estimator under the broad title of statistical inference. So, statistical inference has three different terms, and basically we start with the point estimator. So, a likelihood function or a data point, data distribution can be represented in a mathematical form, which may be combined with, which may be characterized by one or more than one parameters, which are unknown random constants. So, once we are able to estimate them using the data or the samples, then we are supposed to evaluate its performance. Hence, there is a need to understand the metrics for evaluating point estimators. So, generally we simply say here methods for evaluating estimators. So, the contents for the discussion, as I mentioned, two important metrics: mean square error, they call it as MSE, and another one is through the variance, and in particular we are going to talk about minimum variance. So, this may be the metric we try to say, and this will be qualifying that. So, within this bundle we will have one more part also. So, in the discussion we will include that particular part, which will be part of defining this MSE, stands for mean square error. So, as we observed, this mean square error, the three terms, I deliberately read it so that we understand what we try to do. If we take the word from the right to left, that means I take the error, and then, so error is, in a common sense, error is what I try to estimate and what the actual value is supposed to be. So, naturally the difference is what I try to say error, then you can square it, then we try to find out mean. So, the process is very clearly and directly pronounced here by the term mean square error. And similarly here also, the variance is the way we try to understand a measure for calculating the variability or understanding the variability. So, it has to be minimum logically, so that we may understand the consistency of the estimator. So, variance is generally to refer a consistency of the, if we look at any data distribution, we try to understand how much it is less varied, so that we can say it is more consistent. In that sense, generally variance is looked for that. So, in the same sense, we are also looking for minimum variance. So, the both terms are quite meaningful and straight away one can understand. As I mentioned, there is one more term, probably I have not mentioned in the content, but this will be part of the discussion today to start with, and automatically it will be included in the mean square error also. Hence, I start with this particular term, bias. Let me start with the parameter theta, and we have an estimate and we call it as W. So, what we call it as bias is the expected value we calculate and then get the difference from the actual value what is supposed to be. Anyway, with this we do not know, but we try to estimate this our estimation should be as close to the original value, that is the expectation, that is the supposition. Then our common sense says we are almost try to near the value of theta. This is a little a surprising results or combination, because we do not know theta and we try to estimate through an estimator, say W, and then we calculate a long run average, what we group it as E of W. Then that E of W is actually calculatable, we have through samples, therefore E of W is mathematically calculatable. However, theta is still unknown. In the beginning of the session I told you it is an unknown constant, therefore when we look at this formula as a mathematical expression, then one quantity we may not know what it is, but the other one we are estimating and then we calculate the long run average. But still we have some brevity to define the bias as the long run average of your estimator minus theta. Ultimately it is the difference. So somewhere the original value exists and we try to near, not in a particular instant, on a long run. That means over and over that sample is repeated, we take the average of that estimator W, then we try to calculate them. Put it in a simple framework, maybe with an example. Suppose I do not know what is the average marks of a particular subject in a university, let us say. So that may be the population, or in our terminology we may be interested in noting down theta. However, there may be or there could be enough sample, so that I take a sample mean for that, which we observed that sample mean for such a normal population is a estimator for theta, that is population mean. I can calculate this, then a measure should take as close to as possible. That is how I am calculating. So if this is deviated, then I have some bias. Therefore, it looks like a well defined formula, but still there is a quantity which we may not know. So bias ultimately is a function of theta. And finally, we have a clear definition. If bias of W is 0, that means this expected value is exactly equal to theta, then W is called unbiased. So almost this particular slide or the terminology are very much self explanatory. So bias is the difference. If they are not, if there is no bias, we call it as unbiased. So bias of W should be equal to 0. Indirectly, expected value of theta, the long run average, should be made equal to theta. So in this case, this we call it as an unbiased estimator. Therefore, a quantity we are able to talk about first as a metric to say some quality about the estimators. Okay, so the unbiased estimator gives you some characteristic of an estimator, so that expected value of W will be equal to theta. Now we go to the main point or main content. We try to say MSE, mean squared error, and in a similar terminology I quickly run here W minus theta, we calculate the error. So look at the way bias is defined on long run difference, but here systematically we calculate the difference W minus theta. As I told you, we calculate error, square it, okay, and then I take mean, that is a expectation, that long run average, that is expected value of. So as I told you, this term is a very much self explanatory, provided we understand what it calculates. We want to calculate the error, square it, and then calculate the average. The squaring concept is very much direct, or it is very self explanatory again, because we may expect that the W may go, or it may go beyond theta or sometime less than theta. So on an average, if we calculate simply the difference, exact difference, then we may nullify that value. So we square it to remove the sign, and then we calculate its average. So whether any other such measure can replace this particular item, yeah, like a absolute or modulus value, absolute function, if you replace that, still the similar kind of metric can be computed. So however, here we follow square of the error and then mean. Once again, MSE is also a function of theta. So any increasing function, that is what I say, like absolute distance could measure the goodness of theta. The ultimate aim of this metric should be how good my estimator is, so that we can depend on the method which we coin as an estimator of a parameter, maybe univariate or a multivariate. So, in this discussion I do not make much difference in this case, but generally talking about W is an estimator because it involves a calculation part, and what you calculate as a numerical value, it is generally called as an estimate. So, bias and this mean square error, how they will be connected. So, as I told you, this MSE will have a component with the help of bias, or a component which has a bias. Now, we try to understand how it is going to be. So, mean squared error will incorporate generally two components. So, what are they? Let us have a clear idea. I start from MSE, that is going to be expected value of W minus theta the whole square. So, I have just a arithmetic work, not much. W minus expected value of W plus expected value of W minus theta the whole square. So, nothing more, I just add and subtract this expected value of W. So, remember W is an estimator. So, we will group them. W minus expected value of W square, can avoid this too many square, but anyway A minus A plus B whole square form, then plus expected value of EFW minus theta the whole square. So, we group this term plus 2 times expected value of W minus expected value of W. So, first term into second term. So, anyway the third term by this expectation you will get 0, and this will be EF W minus theta the whole square. This is expected value of W minus EFW the whole square, which is nothing but variance of W. So, variance of W we have, and this if you look at, this is bias square. So, we have two components. So, the two components are variance of W. So, put it in the simpler form or the notation V of W, so which stands for variance, and then square of bias. So, mean square error can be calculated using variance of W plus bias square. So, we are able to minimize our idea to variance. If we observe the two metrics we are talking about, we are connecting with the minimum variance, but I take variance first. So, here also if you observe closely, though we define mean squared error by the way it is called, we boil down to two important components, variance of W and square of bias. Here one more observation we can make interestingly is, what happens if this quantity, namely this bias is 0. In turn, or precisely what I try to say is, what will happen if W is unbiased? So, if W is unbiased, if you observe, this bias term will become 0, therefore, MSE is systematically equal to just variance of W. So, we are able to understand in what way we try to define mean squared error. So, it has two components, and for a special case, if you observe for unbiased, just now we observed that bias is going to be 0, therefore, MSE will become simply variance of that estimator. Therefore, responsibility in the case of MSE lies largely on finding out variance of W, provided we are able to get an unbiased estimator. Therefore, it is a very much sequential calculation, or I could even say it is a responsibility. We are not simply coming out by calculating or estimating a procedure and then stay away. We are having a very logical and sequential responsibility to say my estimator has this much quality. Okay, so that is what our title says. It is a measure for evaluating the estimators. We are trying to say. If you look at closely, once again, bias is one way we try to assure our quality, and another case is MSE. Therefore, all the calculations or all the form are based on how your W behaves. That means what could be its mean. So, you could find out here expected value of W. Secondly, you could observe variance of W. Therefore, the responsibility is once we get an estimator, we try to go further to understand minimum its mean and variance, so that how it behaves. Fortunately, if we boil down to unbiased estimator, MSE is straight away the variance of W, thereby you can give the yardsticks how much it is variate, and then you can stick on to the quality of the estimator. Therefore, the example which we are going to see now will be starting from an estimator, then we go for its mean and variance basically. To start with a simple example, most widely used, I could say even an obsessive for sample mean, that is the basic examples and fundamental points to understand these kind of expressions. Okay. So, I start from an estimator, so that how to find out variance of W and expected value of W. Let us take a distribution which may from IID Bernoulli's theta. So, x bar, which is going to be the MLA of for the unknown parameter theta, which is sigma xi by n. So, this is an estimator. In our continuity of our symbol, I may say this is W, or more precisely this is W of x, a function of sample. So, to understand, I just make it as W of x, or continuity we can use W also. If I calculate expected value of W, so what it will be? It is 1 by n times, so I use this formula, expectation of summation of xi, and the independent rule will permit me to say it is summation of expected value of xi, and identical also. So, 1 by n times theta. So, you could see this is a Bernoulli's form, therefore, mean of x is a theta, and we have n times, so n theta, so it is. So, what we observe, expected value of W is theta. We have a unbiased estimator. Expected value of W is theta, which is what we are expected to say as an unbiased estimator. So, naturally what will happen, this calculation will lead to me, if I continue this calculation, this observation is important. Therefore, if I do further, my MSE will become simply variance of W. So, that is the advantage if we are able to, but this is not compulsive, this may not happen always, but still we have some quick answers to understand our terminology. Now, once I get this, as I told you, I just go for variance of W. As before, I take variance of 1 by n into summation of xi. So, once again formula based on the variance is 1 by n square into n times variance of xi. So, it is 1 by n square into n times theta into 1 minus theta. Anyway, n gets cancelled. So, theta into 1 minus theta by n. So, when n is large, obviously this is going to be small, thereby I can guarantee my variance is small. But anyway, I do not extend that part here, but how to get the quantities which we are interested, mean squared error for an unbiased estimator. Otherwise, we will have to calculate bias because we may not have exactly equal to. Therefore, the difference we have to incorporate here and square it, you will get MSE. So, this is a simple example for which you can calculate basically the bias and variance and ultimately the mean squared error. However, the example is very fundamental and simple, but here we are using heavily the way the distribution of x bar is being used. So, we are not following very seriously what is the value or the distributional form here, but still in some cases it is quite important how do we calculate the variance also. In some cases it may not be so straight, we are getting variance for that. If we take another example for normal with theta comma sigma square, understanding is sigma square is known. So, we must have an unknown parameter which I follow from beginning, theta is going to be the parameter. So, what is my estimator here? My sample mean x bar once again. So, a similar calculation will yield me. I do not go much into that detail because just now we derived mean of if I have sample mean, its expectation is theta straight away, and variance of w we can find out here. So, variance of x bar, which is variance of 1 by n times summation of xi 1 by n square into n times variance of xi 1 by n. Variance of xi we have sigma square in this example. So, 1 by n square. So, once again we have an unbiased case, okay, and I limit my MSE with variance itself because the form we know. So, one more example, and there could be many such distributional form univariate, and I assume deliberately here theta is unknown and sigma square which is known. So, these assumptions are important, otherwise it is not possible. Had it be considered as unknown, then we would have two parameters and corresponding calculations are vital. So, this is another illustration, so that same sample mean would be a component for our problem. One is following bias calculation together with that, but the format will be different because our family is different, and hence the corresponding component of sigma square by n will be presented here. The next case, the same family only x1, x2, etc. xn, but now I will slightly change this theta. That means this I take mu, and here theta I say theta is my variance. So, this normality will help you to calculate this problem specifically, but not in general. I will tell you first of all the calculations involved in this normal, especially to know about the variance part. So, I will be dealing with two. Number one, sample variance. So, S square, which is 1 by n minus 1 times summation of xi minus x bar the whole square. This part can be calculated from the sample. X bar is a sample mean, and we calculate it, finally we reach this form. In a similar way, we can have MLE of this sigma square is sigma square hat is 1 by n summation of xi minus x bar the whole square. So, there is a small difference, therefore, 2 can be approached from 1 obviously. So, sigma square hat is, if you observe, n minus 1 by n times s square. So, two estimators now we have. So, I suddenly jumped to this problem because a parameter can be estimated using more than one estimator. So, we could have a comparative necessity, we may have to compare the performance of one estimator using the other one. Therefore, the procedure for or the metrics for evaluating the estimators also allowing you to compare based on a criteria. So, that would bring you whether it is possible to compare them and then say one is better than other, because we may have more than one method to get estimators which may be different. For example, if we consider an estimator procedure like method of moments, another one like MLE, maximum likelihood estimator, those two answers may be different. Sometimes they may not have any common relationship like what this particular formula or form share. Two estimators share a common relation. In some cases it may not be possible. So, this is something like a intuitional form. This we get it from the very systematic form of maximum likelihood method using the calculus approach, but you can easily observe that MLE is straight away related with the sample variance using this form. Therefore, which one I can prefer? There may be a comparable or comparative platform, so that one method may be better than in another by some sense. Should we have to compare them? That is why I take this example, where you can compare their performance using a metric called, or using a procedure we could say, shall we have method which may possess a property of minimum variance. That is the second metric we were talking about, but I just drag this particular calculations because where do we get a necessity to compare their variance? Otherwise, the concept of minimum variance may not have any meaning. Why should I have a minimum variance, or where do I stop? So, some yardstick can we have. The idea is, if there is a possibility to get more than one estimator, we have a systematic comparison between them. So, one procedure may be a minimum variance. For that, I started with an illustration where two methods, maybe I call it as W2 and this I call it as W1, both are somehow related. Okay. So, this is not something like an approximated, but I just to write they are related. If I know expected value of first estimator and variance of my first estimator, then using this relation I can calculate same thing for second estimator also. Obviously, this may be smaller, I may try to pick, because it is talking about variance which is normally expected to be smaller. So, it is all as I told you, somehow it is some common sense of choosing the statistical metrics. So, always statistical concepts will have mathematical derivations and mathematical form, and then it allows you to think which can be chosen, so that we have further responsibility to stick to a particular metric. That is why I just introduced this idea. So, we continue here this minimum variance. An estimate of a parameter theta W star is a best estimator of tau of theta if bias of W star is 0. So, we group into an unbiased form. Then as I told you, if variance of W star is less than or equal to variance of W for any such W, then this W star is called minimum variance. It is also called uniform minimum variance unbiased estimator of tau of theta, any function of parameter in fact. So, the idea is we grouped into a unbiased set of estimators, and then we are looking at whether it is the minimum most one, so that I call them uniformly minimum variance. So, the words are very self explanatory, but where to start? I have a parameter, I have a function of it, I am estimating it, which may be unbiased, possessing minimum variance throughout the family of such estimator. So, that is how even uniform minimum variance unbiased estimator of so and so can be understood. Okay. So, where to start and how it can be qualified to call it as uniformly minimum variance. Therefore, the last part or last metric what we observe is a responsibility. In fact, I could say if we have more than one estimator, it provides a comparison among a certain family of estimators called unbiased estimator. So, this entire discussion boils down the computation of some metrics like mean and variance of the various estimators what we try to do for a parametric family which is characterized by one or two parameters. So, summarizing, the mean square error which we observed clearly how it is coined from right to left reading, error part and squaring it and then mean. And why do we concentrate on variance? That also we have observed from two components of MSE, variance and bias part, in which we are highly emphasizing the importance of variance, and moreover there may be a possibility to compare them, in which case I may be looking for minimum variance. Particularly we try to see minimum variance and another family of estimators called unbiased, so that I try to combine them to call uniformly minimum variance unbiased estimator of a parameter or a function of parameter. Following that, you can find some examples in the basic parametric distributions beta, and we have estimated using very similar problem. So, I just say repeat it, and similarly you can calculate estimator from method of moment, you can calculate variance, bias and obviously the MSE of this estimator. Thank you for joining this discussion.